Hello, and welcome to the AI Research Roundup. I am Alex, your host. Today is May 10th, 2025. We are looking at a research paper from Hugging Face's trending list, published just 5 days ago, RetroInfer, a vector storage approach for scalable long-context LLM inference. This paper presents RetroInfer, a system helping large language models handle long texts efficiently. It exploits attention sparsity, the idea that models focus on just key prior information, and reconceptualizes the key value cache, or KV cache. This key value cache, storing vital context, is treated like a vector storage system for faster inference. Alright, so this first figure gives us a visual for how large language models, specifically their transformer architecture, work with that key value cache. The transformer architecture is the fundamental design for many advanced AI models. It involves processing inputs through layers that generate queries, keys, and values. These are special representations of the text. We see two main phases in the figure. Pre-filling, where initial text like I love is processed, and then decoding, for processing subsequent words like systems. The diagram then zooms into the attention computation. This is where the model uses these queries, keys, and values to calculate attention scores, which basically show how important each word is. Okay, building on that attention computation, this next figure 2 really highlights what the authors call dynamic sparsity in attention. The top graph shows attention weights, which indicate how much the model focuses on different words or tokens from the input text across various token position IDs, which are just the locations of these words. We see that the important tokens, those with high attention weights, change at different decoding steps, that is, as the model generates more of its response. The bottom graphs, showing the cumulative distribution function of attention weights, confirm that a few tokens often capture most of the attention. This dynamic sparsity underpins the challenge RetroInfer addresses. So, to tackle that challenge of managing the key value cache with dynamically important tokens, Figure 4 lays out RetroInfer's architecture, which treats this cache like a vector storage system. We see two main parts, the wave index and the wave buffer. The wave index, an attention-aware vector index, uses centroids. These are representative vectors on the graphics processing unit, or GPU, to quickly find important key and value vectors from the larger store, often on the central processing unit, or CPU. The wave buffer then efficiently moves these vectors, coordinating between GPU and CPU memory. This design is crucial for handling long context effectively. Okay, so diving deeper into that wave index from RetroInfer's design, Figure 5 illustrates its attention-aware design. It divides the context into segments, smaller text portions. Tokens are then grouped into clusters by similarity, each with a centroid, a representative vector for the cluster seen in the meta-index. The figure highlights how some tokens are in a steady zone, meaning they are always kept readily accessible, while others are in estimation zones. For these estimation zones, their attention contribution is approximated using these centroids, which is a clever shortcut. This approach, combining direct retrieval with estimation based on token importance, is key to the wave index's efficiency. So this attention-aware design of the wave index, with its clever use of centroids and zones, is really what allows RetroInfer to shine. The core idea presented is RetroInfer, a novel way to handle the massive key-value cache in large language models. By treating this cache like a smart vector storage system, using efficient vector search techniques within its wave index and wave buffer, RetroInfer achieves impressive speedups, up to 10.5 times faster in some cases, and maintains high accuracy, even with very long texts. It really tackles the memory and speed bottlenecks. Thanks for tuning in to the AI Research Roundup.